Enrico and Enrique, the saga of the high performance twin brother continues. This presentation was presented at the 2023 IBS show in Las Vegas, where I was hosted by NAHB and the High Performance Construction Group. So I want to thank the organization for putting this together and hosting me this year for this presentation. Presentation that was not approved or reviewed by NAHB, and the content and the statements are our own opinion as EMU and myself. And again, I thank NAHB for hosting me and my presentation at the 2023 IBS show in Vegas. I am Enrico Bonilauri, the co-founder of EMU Passive. I'm a registered Italian architect, and I'm also a Passive House consultant, trainer, and certifier with the International Passive House Institute. Here you see my handle for Instagram as well as the URL for my LinkedIn profile. So please do reach out and get in touch with me if you want to. EMU Passive started off as an architectural practice back home in Italy in 2008, and we moved the company to Colorado in 2016, while at the same time we moved away from designing buildings and we mostly focused on builder training. Builder training focused on the International Passive House Standard, which is a performance-based standard that allows to achieve much higher indoor air quality, thermal comfort, resiliency, and durability by means of the building envelope being built a lot better than code minimum requires. We do that in terms of higher insulation, much better windows, much better air seal, heat recovery ventilation, and avoidance of thermal bridging. And this, as I mentioned, not only gets the building to be a lot more comfortable, have higher indoor air quality, and be more durable, but also it achieves about 80% reduction of energy for heating and cooling compared to a brand new building built according to the 2021 energy code. So we basically teach builders how to achieve that. And as of 2022, we have become the main training providers for passive house builder training in the country. We've done that by taking the training on the road. In the map that you see in the background, you see just a few of the locations that we hit over 2022 and 2023. So we are taking training to where the builders are, and we are adapting the training to the local needs and local climate specific conditions. To begin this presentation, I think it's important to have some values and goals in mind, starting off with a quiz. Why do we put numbers on money bills? We have a money bill on the left showing George Washington and a money bill on the right hand side showing Benjamin Franklin. Now, in my opinion, George Washington was a much better person and more important for the country than Benjamin Franklin ever was. In fact, George Washington was the first president. And so to me, the money bill on the left hand side has much higher value, in my opinion, than the one on the right hand side with Benjamin Franklin. And so I would propose a deal. If we have no numbers written down on the money bills, I will give you a George Washington in exchange for maybe two Benjamin Franklins from you, because in my opinion, George Washington was much better than Benjamin Franklin. Now, if you're familiar with money bills, you know that George Washington is on the $1 bill and Benjamin Franklin instead is on the $100 bill. So you would understand that one George Washington in exchange for one or two Benjamin Franklins is not a great deal, because you will be losing money. So we use numbers, we show numbers, we print numbers on money bills because numbers matter. Opinions only go so far. So we need numbers in every day of our lives to make informed decisions about buying bread, getting anything done. So we use numbers on a daily basis. And I want to show, and in this presentation today, I'm going to cover how the same numbers are important to evaluate if option A for that project is better than option B or C. Something that if you come from a prescriptive approach that what is building code has gotten us used to, then you may not be that familiar with. We're going to see a lot of examples of performance of products, expectation that we meet and set up with our clients, and how we want to deliver on that expectation. So numbers help us throughout the process, and it's something that we're not that used to seeing in construction. On a similar note, and continuing with the quiz time, let me ask you this question. In average, how many years you think a family stays in a house before they move out again? How many years is a family going to stay in a house they just moved in before they move out again? Think of a number. Now, you got that number? The average builder, or most builders, believe it's 5 to 7 years. Is that close to what you had in mind? Now, the reality is that that number is actually 13 years, according to NAHB data. So this is what the market actually is, according to the statistics put together by NAHB. That means that most families stays in their homes 2 to 3 times longer than most professionals believe. Most professionals that actually advise them on if they need to renovate the building, if they need to replace the old windows with new, more efficient ones. So the market is warped by this belief that is not based on data, and this belief causes underperformance because you really want to match what you're recommending with the actual reality of the market. That family, statistically speaking, is going to stay in that house 13 years in average. And so when you are making recommendations to that family, you need to base your recommendation not on 5 years, but more than twice as long, that is 13 years or longer. So it is our job, because we are the professionals, we are the ones supposed to know the data. It is our job to keep up with the data. And throughout this presentation, I will provide data to show how different products perform and how they perform at day one as well as after 13 years, and see if it is worthwhile or not to invest or to recommend doing to execute certain works and over others. This is crucial because this is how we make informed decisions. I'm saying that because the moment we have a budget to spend, we're going to have heaps of people wanting to help us spend money. Achieving those goals that we may have is a different thing. We're going to spend that money, we may not get the value we're trying to get. So science, whether you want to get to the full passive hours or not, but the passive house science provides us with means to quantify if A is better than B, not just because I saw that on a video on Instagram, but because A gets us 10 degrees higher temperature on the windows, that is higher comfort, or it gets us much better indoor air quality, or it gets us 35% less heating and cooling, or maybe 80 or maybe 90% less heating and cooling. This is something we can quantify, and we can allow clients to make much better decisions that are much better informed than just, I saw this product, it looks good, let's try. We are the professionals in this conversation. Our job is to have this information to allow our client to make better decisions. We work in a market where there is a minimum, in most cases, uh, that is provided by compliance with code. Code gives us guidance as far as how to build a building so it's not going to collapse, so it's going to be structurally sound, so that it's going to be safe from fire, safe from flooding, from water and whatnot, as well as is going to have a minimum level of energy performance. And that is the baseline in this conversation. We have a code minimum that we need to meet, otherwise it is illegal to build. So literally, the code minimum building is the worst building that you can legally design and build. That is the baseline. You cannot do worse than that. Now, on the other side of the spectrum, we have the Passival standard, the international Passival standard, that is recognized to be the most stringent standard out there in terms of comfort, indoor air quality, as well as energy efficiency. In fact, in terms of heating and cooling, passive house can, in average, allow for a reduction of about 80% of energy needed for heating and cooling compared to a brand new building built to the latest energy code that is the 2021 IECC. 80% less. Think about having less photovoltaics because you need a lot less energy. Or if you want to have that PV system to then power your electric vehicle instead of having your house eating that up. That is a significant improvement in efficiency. But anyway, these two, code minimum and passivals, kind of represent the two ends of the spectrum. And in between these two ends, we see a variety of terms that we have a very hard time understanding what they are, but they circulate plenty of, starting from my building is better than code. My building is much better than code. My building is high performance. I've been doing this job for 15 years. I cannot pin down what high performance means because you can literally have a quarter of an inch more insulation than code minimum and call that building high performance. Literally. So it means literally nothing. My building is super tight. It's super insulated. It's a zero utility house. It's so good. It's passive solar. It's basically passive, but we haven't done the modeling. Now, all of these terms are so confusing and they circulate freely and constantly in the construction industry, which makes the conversation much foggier and difficult to understand for everyone. I'm not saying the passive house certification is the answer for all projects. What I'm saying is that we want to have clear expectations when we start off on a project, because based on that expectation, we define success, we define failure, and we have an expectation set up with the client to meet. It's a promise that we meet, and we have to deliver on that promise. Now, take a step back from the construction industry and think about this. You go to the hospital because you have this. Your arm hurts and you want to get an answer. And the answer you get to the hospital is it's broken, or it's basically broken. It's better than broken. You can see this is the same logic that we have on the left-hand side of the screen for the construction industry applied to the medical field. If at the hospital they told you it's better than broken, you would flip out. You would not accept that. In the construction industry, we get all of these fuzzy definitions that mean nothing, and we are okay with that for some reason. Now, there is a risk with that, and we call these intermediate obscure terms super tight, so good, better than code. We call these floaters because they float between the minimum of code compliance and the maximum of passive house certification. And again, I'm not suggesting to certify every single building. What I'm saying is that we have two standards, code and passive house, that are very clearly defined. You can go online and find the definition of code or the definition of passive house and follow them. And by compliance or by certification, you can have certain expectations and goals. Whereas if you are floating in between, it's very hard to manage because you have undefined expectations which do remove structure. It makes everything harder to pin down. I heard from the client that they want this window because their cousin told them it's better performance than XYZ. Now, for code compliance, we have a maximum allowed U value. For passive house, we have what is called the comfort requirement that drives the selection of windows and doors. And anything in between, if you remove those two, you are guessing. You are tossing a coin in the air and trying to catch it and see which direction to go because you just don't know. The risk is to overpromise and underdeliver, to overkill or overpay. There's many risks with this, which all come down to the expectation is not well defined, and it's very hard to meet or deliver an expectation that is not well defined. Now, this is an example from the UK of monitoring the energy performance from multiple buildings over the years after occupancy and seeing how they were delivering the performance of energy efficiency that they started off with from the design. So we have a promise that is the predicted or expected energy consumption, and then that is the salmon pink part of these columns. And then the darker maroon red is actually how much more these buildings, how much more energy these buildings were consuming because they were not meeting the expectation. There's a performance gap between the energy consumption that the design expected and how much energy they're actually consuming. And in this graph on the right hand side, we see three passive house projects that actually where the gap between predicted performance and measured results is so small that it's basically negligible. So this is the point I'm trying to make. We are making a promise to our clients that we need to deliver on that. And if we don't have a clear structure to follow through the design and construction stage, we are very much at risk of not delivering on that and having very unhappy clients because the delivery did not meet the expectation. So to give an example of a project, I don't know if you've seen the previous presentations for Enrico and Enrique. I do this presentation based off of the climate of the location where I'm giving this presentation. This presentation specifically was set in Vegas. So I set this presentation up for the climate of Vegas. We have other climate zones for locations that I've given this presentation to in the past for Texas, for Tennessee, and we have more for colder climates coming from in Maryland, in Minnesota in the near future. So stay tuned and keep on following us on YouTube. At some point, I'm going to get good enough to put links to that in this presentation. I don't have that, but you'll find that in the description to this video. So Enrico and Enrique is a story of two twin brothers addressing the two very similar projects. So this is Enrico, sorry. And Enrico has an accent, if you cannot say. It's a total square, and he's contracted to build a high-performance house. And Enrique is what everybody here in Colorado calls me. So at some point, I decided to make up an evil twin brother of mine. so that if you call me Enrique by mistake, you're gonna get the evil twin, and you're gonna pay for it. I am not kidding. Enrique also has an accent, Googles a lot, and he's contracted to build a house better than Enrico. So we're gonna see how Enrique is gonna go above and beyond to beat Enrico throughout this presentation. To meet the client expectation, we're gonna have different steps, and we're gonna see if we're gonna deliver on that promise. Now we have a project that is my house up in the mountains of Colorado that I have conveniently moved the energy model to Las Vegas to perform the analysis. And Enrico and Enrique are contracted to build two different buildings almost identical to one another. Same floor plan, same elevation, same building sections. They're just going to tweak different details to get to their goals. And because this is Vegas, it's time to have some rooftop celebration before we get started. Starting off from the building envelope, Enrico has done the modeling, and for the slab, decides to use no insulation on the slab. At the end of the day, Vegas is in a hot climate, so Enrico thinks he can get away with that. On the other hand, Enrique thinks we want to have insulation on all sides, so he decides to use 3-inch of XPS on the slab. For the exterior walls, the goal is to have R30. Enrico does a wall assembly starting from the inside with drywall, then spec cellulose in the 2x6 cavity, get it to R20, then the plywood sheeting, 2-inch of polyiso exterior as continuous insulation to get an R12, and then the rain screen system. Whereas Enrique does something similar but a little bit different in that he has the drywall, has the dense spec cellulose in the 2x6 cavity, and then the R12 zip R sheeting, not sheeting, I'm sorry about that, the sheeting, and then the rain screen. For the ceiling, Enrico uses 15-inch of dense spec fiberglass to get to R60 and has a smart vapor retarder on the interior, whereas Enrique uses 8.5 inches of closed cell spray foam to get to the same R60. Then for windows and doors, Enrico thinks he can get away with double pane glass with 90% argon fill and uses an INI window install detail where the window is lined up with the center of the insulation. That is what it looks like in the section drawing. On the other hand, Enrique uses a triple pane because he wants to go above and beyond Enrico. Although Enrique has found online that the argon fill escapes only after a few years after install, so that's not worth it, and sticks to the air fill instead of argon, and then uses a more traditional Audi install where the window is lined up to the exterior in a more conventional install detail. Then for fresher system with heat recovery, Enrico uses a centralized ERV that is ducted to the individual rooms with 87% heat recovery, whereas Enrique uses ductless HRV with 89% heat recovery, so a little bit less, a little bit higher heat recovery for Enrique. Air barrier, the target is to get 2.6 air changes per hour at 50 Pascal. For the slab, Enrico uses the polyethylene membrane that is the vapor barrier. He seals that at all seams and penetration, and that is the air barrier under the slab. Then uses the sheeting sealed at all seams for the walls as the air barrier. And finally, at the ceiling, he uses the smart vapor retardant membrane as the air barrier. Enrique does something different. For the slab, he uses the same poly membrane as Enrico does to be the air barrier. For the walls, he uses the sheeting he uses the drywall taped all seams as the air barrier, and then at the ceiling, the closed cell spray foam is itself the air barrier. Enrique also goes above and beyond in that he hires Aerobarrier to get to that zero point 0.6 air changes per hour. Now, if you don't know Aerobarrier, that's a company that has a product. Basically, they nebulize and spray sealant agent in the air inside the building that goes and seal uh, all the cracks and makes the building airtight. That is a game changer, in my opinion, for retrofits where you don't get to pick and choose your framing and your sequence with your air sealing. But we're gonna see what that means to get to 0.6 with Aerobarrier for Enrique in this presentation. It's time to build. Starting from crunch, 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 get to the construction, yay. And eventually we do the blower door test. Enrico gets to 0.6, yay. Enrique also gets to 0.6, yay. Funny story, I couldn't find a Lego version of the blower door test. So Lego, if you're listening, that's a good hint to educate our kids about the importance of the buildings being airtight. But anyway, both buildings get to 0.6, and that's awesome. So this is the expectation we have. Enrico this graph shows the expected energy consumption for heating and cooling over a typical year. Left hand side is Enrico, and right hand side you see the column is lower because Enrique has put in all of this extra, the XPS and the slab, the triple pane, the Aerobarrier, blah blah blah, but didn't do any of the modeling. So, but the expectation is to have Enrique expects that to be 30-40% savings, less energy consumption compared to Enrico, but hasn't done any of the modeling. And this is awesome. So we have hit the indoor air quality target, we have thermal comfort, moisture control, high energy efficiency. It feels so good. I'm so proud. I'm gonna tell my buddies about this project. Happy, happy, joy, joy. Puppies, kittens, yes, meeting expectation, rainbows, everybody happy. Until day one kicks in and we start looking at performance. And Enrique's building is actually consuming a lot more energy than anticipated. You see on the right hand side, we make the same colors as the study in the UK, and the dark red color on Enrique's column is the extra heating and cooling that is building is causing because it's underperforming. So there is a gap between the expected performance and the performance that was actually delivered. On top of that, Enrique's building also has condensation issues, which is something that clients get really mad about. So let's see what went wrong, and keep in mind that this is for the climate of Vegas. So something went wrong, we want to find out what it is. The C word is, in construction, condensation. Look, and this is very important where we need to start looking at details very closely, because the more buildings become airtight, and the closer we get to buildings consuming zero energy, the more every single little detail matters. Enrico used vinyl flashing as a drainage plane under the windows, whereas Enrique thought vinyl is not sturdy, so he wanted to use steel, and we modeled stainless steel. You have a picture on the right hand side here from a job site, and we see that all the time on Instagram and social media being called out as high performance details. Like, to me, and in my experience in doing energy modeling, that is not a high performance detail, that is an eyesore. Because the moment you start looking at the isotherms of that detail, you see the problem. Now, the isotherms are, when you look at the thermal model, right hand side is warm because it's inside, left hand side is cold because it's blue, it's on the exterior, and those black lines going along the model, those are the lines with the same temperature. Those are the isotherms. And we look at those to see how temperatures distribute over the detail. And you see that at the top, in Enrico's detail, those isotherms flow from the glass at the top nicely down through the frame into the wall assembly below. Whereas for the Enrique's model at the bottom, we see that they go from the glass down over the frame, and when they hit the steel, the isotherms are not happy. They fan out like it's a T-shaped mushroom, and that is a sign of a very unhappy isotherms. And that leads to, this is one piece of the science of passive house, the temperature factor. And if your temperature factor, I'm not going to expand on what the temperature factor is. We have articles on our website that you can look up. But if the temperature factor is too low, it will lead to condensation, which is what is happening in Enrique's project right now. So again, these details with the seal pen or threshold pen being steel and cutting all the way through under the frame, those are a no-no in high performance airtight buildings. So again, we need to rethink about how we do details to prevent this. Then looking at different elements of the performance. Enrico used double pane glass filled with argon, whereas Enrique used triple pane. So triple pane is always better than double pane, right? That's wrong, because it really depends on how the performance of the glass is. These two columns here show the R value, just like the R value of a wall. This is the R value at the center of the glass. And in this condition, the double pane performs better than the triple pane, because there's a if you get a triple pane that is too skinny, in this case we call skinny a 1 inch overall thickness of the glass unit, then the glass is going to underperform. On top of that, Enrique has only air fill, whereas Enrico has argon, which insulates better than air. We're going to see about the loss of gas later down the line in this presentation, but at day one, the double pane performs better than the triple pane. That is because a lot of the glass is rated for very cold temperatures, and in Vegas, those temperatures, you see the graph here on the top, in yellow, you see the temperature the glass is rated at in the US, and those temperature never happens in Vegas, never. So that is, you may have the perception that the triple pane in this case and in this climate performs better than double, but it doesn't. In fact, we modeled some projects, so some glass option for an actual project in Colorado, and the manufacturer was proposing quad pane, thinking that it was going to perform better, and it is more expensive, but actually ended up performing worse than the triple pane, and it costs more because it's quad pane. So you really want to be careful about choosing one product over the other, because you may have a premium, you may be paying for a premium and not receiving the value that you're paying for. A few more causes of performance gap, starting from the zip R sheeting. Now, it's a piece of sheeting which is insulated, but it received the same amount of nails as a piece of sheeting. So this energy model highlights all the individual nails that go through that insulation and still conducts heat over 1,000 times better than insulation. So the closer you get to consuming zero energy in buildings, the more every little detail matters. We really not really count the individual nails, but we account for any metal fasteners going through the insulation in passive house. Whereas for net zero or high performance or any other in-betweens, you don't get to that level of detail in your energy model, and that leads to a performance gap. That leads to your building underperforming. Now, in this case, we have so many nails through that insulation that Enrique loses about 10 to 15% R value just because we have more heat losses through those fasteners. Then at the ceiling, Enrique used spray foam. Now, spray foam performs awesomely in a lab, and in a lab, you can rate that spray foam to be up to 7 R per inch or more. But in the field, it's very hard to get to the perfect mix of temperature and relative humidity. Plus, manufacturers often spec a maximum thickness that you can do for each pass. And if you're doing 8-inch thickness like Enrique, you will have to go back 4 times because the manufacturer requires you to do at the maximum 2 inches per pass. Whereas if you bump up the spray nozzle and do 8 inches in one pass, you're cutting corners, you're going to get to another performance. In fact, the same spray foam in Europe is not rated at 7 R per inch, it's rated at a half of that, at about 3.6 R per inch. And that is the performance that Enrique gets in the ceiling. So instead of R60, he ended up getting about R30, so a lot of underperformance there. Similarly, because Enrique chose an Audi install, his windows underperform. You see the orange dash line in the thermal model of the wall on the bottom left, and that center line is the optimal position to install that window because the isotherms want to go straight through your wall, from your wall into your frame, into your glass. And if we are causing those isotherms to go all the way to the exterior to meet the glass and then come all the way back in to meet the frame and meet the wall again, that is going to cause an underperformance. So that is the same cost for the wall, the same cost for the window, but you get another performance just of the geometry. This is not about the quality of the install, it's about the design of the install. This install detail is designed poorly because the glass should be centered with the center of the wall, R value of the insulation, and it isn't. So that is a cause of the performance loss due to poor design of the detail. This is not yet again accounted for the quality of the install. And you have an example of what an optimal position would look like with the INI install for Enrico on the left hand side, where the center of the glass is lined up with the center of the insulation of the wall. Now that alignment does not to be smack down the middle, but it should be close. Otherwise, you're going to pay a price in terms of performance gap. So Enrique starts to feel very bad about his project. Now, more performance gap in the venting and air sealing. We looked at these HRV ductless units, and they have a nice report saying that they can have 89 or 90% heat recovery. Now, unfortunately, the standard they are rated at, DIN 308, is a poorly written standard, meaning that it does not account for intermittent operation, that is what these units do, and it does not account for the fact that does not account for the energy consumed by the fans in the process. So the least efficient the fans, the more heat the fan lose, the more you believe you have a higher heat recovery because the temperature of the air is higher, but in fact it is the inefficient fan that is actually warming up the air. It is not the ventilation unit actually recovering the heat. So in reality, these units don't perform at 80 or 90%. They actually deliver around 60%, and that is another piece of the performance gap that Enrique has to pay. Similarly, we talked about Enrique using Aerobarrier to get to 0.6. Now, Aerobarrier is a great product, especially for retrofits. On the other hand, the reports they give are misleading in that in the process they spray and nebulize caulking agent, so a sealant. So any windows, any ducts that you have, you need to put masking on to protect them. And that masking contributes to the apparent airtightness of the building, meaning that if you do the Aerobarrier test today with the masking on and you get to zero point 0.6 air changes per hour, then you remove the masking, you're going to have a much higher air changes per hour result, which is shown here on the graph, on the column chart at the bottom right. So Enrique, the light blue zero point 0.6 is the result at the Aerobarrier test, and then once you remove the masking, your number goes up very much to about zero point 0.9. This 0.9 we made up based on our experience on our own projects, what we saw the before and after removing the masking. So again, it's a great product, but the results they give are misleading because they are what we call preliminary blower door test. A preliminary blower door test, you may have masking, you may have windows not installed and whatnot. It's a preliminary number. But the final number, the one that matters, is for when the building is absolutely complete. All the finishes are there, all the appliances are there, so no masking is allowed. And what we saw, the difference between the preliminary and the final with Aerobarrier was a significant increase, which is reflected in this graph. So this we saw a breakdown of all the individual causes of performance gap, and that is what is causing Enrique's project to underperform. Now keep in mind that he paid a premium for that. He got the triple pane glass, he got the XPS under slab, he got the zip R because he thought it was a better thermal break, so on and so forth. And Enrique still got to a much higher energy consumption than Enrico. Now, how something that we don't see much being talked about is how does this high performance age over time? We talked about air tightness. We talked about windows having gas in the glass, about the insulation, all that. How does that age over years? And we looked at 13 years of span because that is the average amount of time that family is going to stay in the house before they move out again. Now, as professionals, we need to move away from what we believe and we need to frame our conversation about the data that we see in the market. Now, you may have believed, or we may have builders believe that the family stays in the house for 5 years, but that is not a professional conversation. That number is actually 13 years, and that is what we used in this presentation today. Now, we talked about argon, and that is what Enrico chose, whereas Enrique thought, oh, that is going to underperform over time because all the gas is going to be gone shortly, so why bother? Now, gas, the argon does go away a little bit. We're going to see how much. Now, at day one, we saw that the double pane glass with argon fill was outperforming the triple pane, the skinny triple pane with air fill. Now, keep in mind that when we work on projects, typically the decision between triple pane and double pane is driven by comfort. And generally speaking, Clemson 4 and higher, we end up speccing beefy triple pane for comfort reasons, not for energy, not for payback, it's for thermal comfort. Now in Vegas, that is less of a problem because it's a warm climate. So Enrico can meet the passive house comfort requirement by just using a good double pane. And whereas Enrique thought that with the triple pane it would be passive house, so I need triple pane, so check, and that is not the case. And he ended up with a skinny triple pane that underperforms compared to a double pane with argon fill. But what happens over time once the gas starts escaping? Now, again, looking at the data, we can expect about 1% loss of gas each year. Now, the glass unit is never going to be 100% filled with argon. If you see a manufacturer that claims 100% argon fill, that is a lie. There is no technology today that allows to achieve and guarantee 100% of argon. Maximum is 90%. Some manufacturers claim 95%, but in my opinion, we stick to 90%. So out of 90%, if we lose 1% per year, after 13 years, we will be going down from 90% argon and 10% air to 77% argon and 23% air. Now, that still outperforms a skinny triple pane filled with 100% air. So we do have a loss of gas over time. If the glass units are well manufactured with the current technology, you can expect that loss of gas to be limited to a 1% per year. And over 13 years, that is still better than having the glass filled with just air. So this is where you don't want to pay the premium in Vegas for the triple pane. You want to have the argon fill, which is actually quite affordable. This is where you may have the perception of getting a better product with the triple, but you're actually buying something that is underperforming. So be very careful about that. Then what about insulation? Now, XPS at day one performs at 5 R per inch. Now, over time, it loses some of its expanding agent, so over time it loses some R value, and that is reflected here. In fact, in our modeling, we use 4 R per inch as our default design value because we want to guarantee the performance of the building over 20, 30, 50 years over time. So that is something that is very important for you as the professional to have, to base your building on the expectation of a certain dependable performance of your product, so that overall performance can get you to a very durable building. Similarly, buildings may become more leaky over time. Now, the oldest modern passive house was built in 1991 in Darmstadt, Germany, and at day one they scored about 0.3 ACH 50, and after 25 years they replaced the gasket at windows and doors because that was considered to be part of the maintenance of windows and doors after 25 years. And then they tested the building again, and they again hit about the same 0.3 ACH 50. So that is, if you choose the right product, that air tightness is something that is very durable. We have literally had buildings that prove that after 25 years, that durability stays there. On the other hand, there are as many buildings that prove that they get a lot leakier over time. And that is the case that we call out here with Prosky in 1997. They tested a lot of buildings that were using drywall as the air barrier, and they found that drywall, the air leakage through drywall, it grows 4 times faster than buildings using air barrier membranes, air sealing tapes, and products that are actually designed to be airtight. And that is reflected in this graph on the left. You see 0.05 increase in air leakage over time for Enrico, and 0.19 additional increase in the ACH 50 for Enrique. So they started off, both of them, at 0.6, and after 13 years, Enrique's building is almost twice as leaky as Enrico. You don't want to do that. You want to have something that is very dependable. So all of this contributes to an increasing in the performance gap for Enrique, and Enrique paid for that premium. So Enrique is very pissed. He's very emotionally charged in a non-positive way about what he did in this project because he paid more for a building that is not performing. So conclusions: The closer we get to zero energy consumption in buildings, the more every detail matters. Um, you'll always find plenty of help to spend your money. Whether you're going to get to your goals is a different matter. And whatever those goals may be, the performance based analysis allows you and your client to make informed decisions. Is A worth it, or is B better because it's cheaper? Is B actually delivering what they are claiming? All of this is extremely important to achieve a higher performance. And Passive House, as an international standard, provides scientific method to prevent modern condensation by means of the temperature factors that we saw earlier, and to deliver higher quality in terms of indoor quality, comfort, and energy efficiency in a way that building code is honestly decades away from enforcing and implementing. So that is why we push to use the passive house science in every project, although they may not be seeking certification, but just a higher quality of living and building standard. Thank you for listening to today, and again, thank you for NAHB and the friends of the Construction Performance Group for having me at the IBS this year and for having this presentation. Thank you for your attention and your time.